Thank you, Mr. Chairman. Morning, everybody. Title of my talk: surface crack growth in cylindrical hollow specimen subject to tension and torsion. This report will be presented on behalf of my colleagues, Rustam Yarovin and PhD students Ivan Ishtoyakov. Outline of my talk is the following. First of all, I will show specimen, material properties and loading condition. Next part is the numerical study, including constraint parameters, behavior determination, plastic stress intensity factor, again determination. Then is experimental results, including correlation between crack opening displacement and crack length on the free surface of cylindrical specimen, then correlation between crack growth rate and crack opening displacement, and finally surface crack growth rate characteristic defined, and finally will be a conclusion. First of all, I would like to start with our early work. We tested a hollow thin walling cylindrical specimen under different loading biaxes. In this figure you can see the curve, limiting curve in nominal stresses under different loading conditions from uniaxial tension, pure pressure, pure torsion, and pure compression. And another two pictures with very interesting types of static fracture. That is the pure compression you see, and three direction loading: compression, compression, torsion, and pressure. So subject for our consideration is the hollow cylindrical specimens which produced from two types of classical aluminum aluminum alloys. In Russian notation is D16T, B95. They're the same analog of American 2022 or 7075. You can see the main mechanical properties, including elastic plastic properties, both aluminum alloys. We tested hollow specimens with wall thickness 10 millimeters, with initial surface flow with different aspect ratio. One of them is the aspect ratio equal 1, another one is 0.3. Loading conditions are, first case is the tension, cyclic tension, another one combined loading and cyclic tension and cyclic torsion in phase loading. So, first of all, I would like to show you some numerical results. For experimental crack front conditioning, we calculate numbers of parameters, including constraint factor, stress intensity factor, and so to this end we use traditional finite element approach to determine distribution all parameters along curvilinear crack front. So, as you know, in literature there are several constraint parameters. One of them are elastic constraint parameters, another one elastic plastic constraint parameters. In this table are listed both. First of all, elastic T stress, then Q factor, and second order amplitude factor in high term expression. And these three constraint parameters are in-plane constraint parameters. Another one is is the stress triaxial TZ factor and AB area are out of plane constraint factors. And in order to determine distribution of all parameters along different kinds of surface flow, we introduced dimensionless coordinates, where R is a parameter which has value 0 on free surface of all cylindrical specimens and has value equal 1 in the deepest or mid sections of cylindrical specimens. Next figure represents the distribution of constraint factor along curvilinear crack front for experimental crack front position, for instance, for uniaxial tension. You see how change T stress from free surface up to mid-section specimens, TZ, that is in-plane constraint parameters, that is out-of-plane constraint parameters, and that is the stress triaxial parameters. As additional parameter, which is, with my point of view, is the general parameter, as I told yesterday, is the plastic stress intensity factor. Plastic stress intensity factor was introduced by Professor Hutchinson. This equation describes some parameters included in plastic stress intensity factor equation. That is elastic stress intensity, yield stress, strain coefficients, and hardening strain coefficients, and hardening exponent. I would like to remember you that plastic stress intensity factor is the amplitude factor in classical HRR, Hutchinson-Rice-Rosengren solution. The problem is that how to determine governing parameters, elastic plastic stress field, for real structures, for instance, specimen, because Hutchinson introduced and gives the values of this parameter only for infinity size cracking body as a function only strain hardening exponents. We elaborated method to numerical calculations for these parameters on the basis of finite element results. In order to determine this parameter for mixed mode loading, you need to exclude displacement as a rigid body. You need to exclude this in total displacement. You need to exclude this displacement. You can see the differences. So, in this figure, I would like to show you the distribution of stress triaxial parameter and governing parameter of elastic plastic stress field along curvilinear crack front as a function of loading condition. Tension, and torsion. You know that stress triaxial parameter, that is the classical analytical solution, is equal to 0, and pure torsion. And at the same time, you can see how changing governing parameters of plastic stress field for the same loading condition. So, and again, I would like to pay your attention on the differences between behavior of elastic stress intensity factor and plastic stress intensity factor. For the same curvilinear crack front, you see the distribution of elastic stress intensity factor under tension loading condition. That is a change of elastic stress intensity factor from free surface specimens up to deepest point on the crack front. And at the same time, for the same loading condition, you see for two aluminum alloys with different plastic properties, you see the different curve for plastic stress intensity factor changing as along curvilinear crack front. So, and now I am going to explain the results at our test experiment. When we carried out our test, we fixed simultaneously the crack opening displacement on the free surface of specimen, and by using optical microscope, we measured crack length on the free surface of all tested specimens. So, and now you can see the. So, during our test, we fixed crack front position by changing R ratio. We fixed the maximum amplitude, but changed minimum value of amplitude stress. As a result, we have got position of crack front for initial cylindrical crack front and another one. And as a result, we have got relation between aspect ratio as a function of dimensionless thickness. For these types of initial flow and initial flow with aspect ratio approximately 0.7. You see when dimensional thickness is equal approximately 0.25, both curves approximately coincide with each other. So now I would like to show you crack passes under tension and torsion loading. And again, crack front position as a function of accumulated number of cycles of loading. So, next figure represents the relation between crack opening displacement and crack length on the free surface of specimen for both tested aluminum alloys and for tension and torsion loading. Next figure is the crack growth rate as a function crack opening displacement. Crack growth rate on the free surface of cylindrical specimen measured by optical microscope and crack opening on the free surface of specimen. You see that approximately general curve for different loading conditions and for different aluminum alloys with different properties. So, and finally, I would like to show you fatigue fracture diagram that is crack growth rate as a function of elastic and plastic stress intensity factor. Open symbols depicts the free surface. Crack growth is on the free surface of specimen, and dark points depicts the crack growth rate in the deepest point of the crack front. You see that crack growth rate are different on the free surface and deepest point. By using the relation between aspect ratio and crack length on the free surface, we obtain the crack growth rate in this direction. So, and our future work. Now I shown you the result of test under room
temperature for both aluminum alloys a bit, but we are going to test under elevated temperature and low temperature, especially for this, because is a relation between crack opening displacement and aspect ratio. So, to the sense, we have used different equipment. So, and conclusion of my talk. It is found that there is one general relationship between crack growth rate on the free surface of cylindrical specimen and crack opening displacement for both tested aluminum alloys and loading condition. In the case, the tension and torsion cyclic loading. Increasing in the crack growth rate is observed in the direction of deepest point of the crack front for both tested aluminum alloys. And it is stated that the elastic plastic stress intensity factor, in my opinion, again, this is a very convenient parameter to present for interpretation crack growth rate data. We take into account plastic properties of